Hello, I'm going to talk about the subject of rolling without slipping. Actually, no slipping condition means that the velocity of the contact point of the object, here I've shown it by point B, is equal to the velocity of the ground, and it's obviously the velocity of ground is zero in most of the problems we deal with in mechanical engineering, dynamics, or vibration. So the velocity of the ground is 0. Obviously velocity of point B should be 0 too. So I'm going to find the velocity, actually the relation between the velocity VO, velocity of the center, and the angular velocity of the object, which is omega. Also I'm going to find the velocity of point B at the bottom and point A at the top, and then later you can find velocity of any arbitrary point on the disk. Before starting this, I'm just gonna remind you that we know this equation, velocity of point A as a vector is equal to velocity of point O, again as a vector, plus V A with respect to O. Here, this relative velocity is nothing but omega cross product r, which is the distance, and omega is the angular velocity, again as a vector. So by using this equation and considering that big R, capital R, is the radius of the disk, I'm going to write the velocity of point A here. So velocity of point A as a vector is VO plus omega cross R. Omega is a vector inside the page, and R is a, for A, R is a vector upward like this. So if you calculate the product of omega cross R, the answer will be to the right. So we have omega R to right. I do the same thing for point B. Velocity of point B as a vector is equal to VO as a vector plus omega cross R, as I explained it here. But this time omega is a vector toward the inside the page, and R is a vector downward from point O to point B. So if you calculate this multiplication, the answer will be to the left, which is omega times R, and because it's to the left, I show it like this. But on the other hand, I know that velocity of point B should be 0. The reason is that the contact here, and the velocity of point B should be equal to the velocity of the ground, otherwise we would have slipping. So this is equal to 0. VB is 0, VO is to right, suppose it's known, and omega R is to left. Obviously value of VO should be equal to omega times R, or omega will be equal to VO over R. This is the equation, always correct for no slipping condition. Angular velocity of the object is equal to the velocity of the center over R, or velocity of the center is equal to the angular velocity times radius. Now if I write the equation for the velocity of point A again, I will have VA as a vector is equal to VO as a vector plus omega times R to the right. If you remember, we calculated it and we found that this is to the right direction. So I can write omega r to right, but omega is VO over r, so it will be VO to right plus another VO to right, so it's 2VO or 2 omega times r. Now we have the velocity of point A, which is twice of the velocity of point O, and then I know that the velocity of point B is 0. Just to finalize this problem, I'm going to show a diagram like this. Usually for a disk like this, we can say that velocity here at the bottom is 0, velocity here is VO, velocity here is 2VO, and we can show them by something like a triangle like this. For any other arbitrary point on the disk, we can use this the equation V of point P is equal to VO plus omega cross r. Omega is a vector, r is a vector, VO is a vector, and VP is a vector too. Suppose point P is here, so vector r is from the center to point P. By using this equation, you can find the velocity of point P as a vector.